We're looking at special triangles and trig ratios of angles between 0 and 360 degrees. And to get trig ratios of angles greater than 90 degrees, we define the trig ratios using x, y, and r instead of the traditional opposite, hypotenuse, and adjacent. These are the two special triangles. I suggest at this point you hit pause and copy them out. Throughout this unit, you want to have these two special triangles in front of you all the time as you're answering questions. What we get from these special triangles are a few trig ratios. If you look here, we have 60 degrees, and across from it is root 3, and the hypotenuse is 2. What that means is that the sine of 60 degrees is equal to opposite over hypotenuse. That makes it root 3 divided by 2. You can confirm that for yourself by using your calculator. You can find the sine of 60 degrees, and separately you can find root 3 divided by 2, and you'll see that they're the same number. From these triangles, you can find the sine, cosine, and tan of 60 degrees, 30 degrees, or 45 degrees. As another example, the tan of 45 degrees is opposite over adjacent. Opposite is 1, adjacent is 1, so the tan of 45 degrees is equal to 1. One last example, the cosine of 60 degrees, which remember is adjacent over hypotenuse. The cosine of 60 degrees is 1 over 2. Okay, at this point, we're now ready to look at finding trig ratios for angles greater than 90 degrees. We need to bring in something new to do this, because traditionally, you've learned about trigonometry where you have a right angle, you have an angle in question, and you have an opposite, a hypotenuse, and an adjacent side. The problem with this is the greatest value you could have for that angle is near 90 degrees. That brings us up like this. If you go beyond 90 degrees, or even reach it, that turns it from a triangle into a rectangle. So we cannot use this old definition to define trig ratios for angles equal to or greater than 90 degrees. So we bring in a new definition. Our new definition is to consider a Cartesian plane. We call standard position a line from the origin of the plane along the positive x-axis. Remember, this is the x-axis and this is the y-axis. So if we have a line starting at the origin and coming out this way, and if that line stops, we call it a terminal arm. That's what your book mentions it as. If we have a line coming out this way, its angle is considered 0. As we rotate it counterclockwise, that angle increases. So here it's 45 degrees, here it's 90 degrees, and now we've gone beyond that. So here it's 180, 270, and 360 degrees. And at 360 degrees, clearly it's in the same position as when it was 0. So I'm going to draw the angle in, and I'm going to call it theta. Now as you can see, this terminal arm creates the hypotenuse of a right angle triangle, where the right angle is here. We're going to call this the y value because it represents the height, and we call this the x value. We typically call this r, stands for radius, because as you can see, as you rotate this, it forms a circle where r is the radius. We can now redefine our trig ratios. The sine of theta is equal to y over r. Y is the opposite side, and r is the hypotenuse. The cosine of theta is x over r, adjacent over hypotenuse, and the tan of theta is y over x. That's our opposite and adjacent. So in this quadrant, and we call that quadrant 1, in this quadrant there's really no change. Y is just another name for the opposite side, and x is just another name for the adjacent side. The advantage of doing this is it allows us to deal with a case where our angle is greater than 90 degrees. Consider this angle here. It's 135 degrees. Okay, so starting again, we always start at the positive side of the x-axis and we rotate counterclockwise. So starting here, we rotate 135 degrees counterclockwise to arrive here. So if theta is equal to 135 degrees, what is the sine of theta? Well, as you recall, we define the sine of theta as the y value divided by the r value. So if I draw the triangle here, this is my y value, this is my r value. A little bit of geometry and you can tell that the angle in here is 45 degrees. What that tells you is that the sine of 135, which is y over r, is the same as the sine of 45 degrees. So we call 45 degrees the reference angle. So the sine of 135 degrees is equal to the sine of 45 degrees. And remember from our special triangle, here's 45 degrees, the opposite is 1, and the hypotenuse is root 2. So the sine of 45 degrees is 1 over root 2. That makes the sine of 135 degrees also equal to 1 over root 2. Let's look again at the same angle and find its cosine. So again, the angle in question is 135 degrees. Our reference angle is 45 degrees. However, the cosine of 135 degrees is x over r. R is always considered positive, but when we go this way, our x value is actually negative. With our x value being negative, if we were here at 45 degrees, we would have sides 1, 1, and root 2. But since we're over here, our height is still a positive 1 because we are above the x-axis, but our distance over is actually a negative 1. And our r value is root 2. So this is still our special triangle with a side length of 1, another side length of 1, and a hypotenuse of root 2. But the x value is negative 1. That makes the cosine of 135 degrees negative 1 over root 2. You can verify this for yourself with your calculator. Find the cosine of 135 degrees, take negative 1 and divide it by root 2, and you should see that you end up with the same number.